The early decades of the 20th century were a tumultuous time for the nation of Germany. After its defeat in World War I and the levying of tremendous reparations by the victorious Allied powers, Germany found herself a nation struggling for security, identity, and prosperity. As dark a time as those years were for Germany and for the world, these challenges and a nation's will to redefine itself fostered a period of technological development the likes of which no single nation may have ever exceeded. One of the most famous and tragic stories from this time is what's widely regarded as the single most influential air travel disaster of all time: the crash of the German Hindenburg Zeppelin in Lakeview, New Jersey in 1937. The Hindenburg was to be a crowning jewel in Nazi technology, a propaganda tool like no other, demonstrating the nation's technological prowess and ingenuity to the world in the form of the largest airship ever to take to the skies. This Zeppelin would obtain lift not from wings like a conventional plane, but from buoyancy provided by a gas lighter than air. There are precious few choices available to get this job done. The most notable are hydrogen and helium. Both form gases under ordinary conditions, and both are made of particles, H2 molecules in the case of hydrogen, and helium atoms in the case of helium. And both are exceptionally light, owing to their very small atomic nuclei. Even though it's diatomic, hydrogen gas molecules are made of the lightest element possible, so it's one of the lightest gases known. When confined to a balloon, for example, hydrogen rises easily into the atmosphere of the Earth, which is made from heavier molecules like oxygen and nitrogen, and of course, it carries along with it its container. Helium exists as a monatomic gas, one which also rises in our atmosphere because of its small size. So, when confined to a suitably light container, helium can produce the same effect as hydrogen, providing lift for an aircraft. So German engineers knew that one of these two gases had to be used to lift a massive structure like the Hindenburg into the air. Helium has the benefit of being chemically inert, meaning that it cannot react because it has a full valence shell and therefore no interest in making bonds to other atoms. Seems like an obvious choice. But with helium supplies limited, and other nations wary of exporting this valuable resource to militarized nations like Germany, the Third Reich had trouble obtaining helium. So it turned to the only available alternative, hydrogen. This was a costly decision. On May 3, 1937, at 7:25 p.m., the Hindenburg was approaching Lakeview, New Jersey, to land after a transatlantic voyage. Just before it touched down, a massive stockpile of chemical energy was unleashed in the body of this airship as an ignition source, which was never positively identified, initiated a chemical reaction that obliterated the largest man-made airship ever to fly. And it all happened in about 30 seconds. Miraculously, only 32 of the more than 100 people on board were killed in this accident. Nonetheless, worldwide confidence in the rigid airship design was shattered by the highly publicized and spectacular crash of the Hindenburg. Aviation history was sent down a whole new path. From the perspective of a chemist, what might be the most intriguing thing about this chapter in world history is this: the reaction that took down the mighty Hindenburg and changed the course of aviation history is one of the simplest chemical reactions known to man: the combustion of hydrogen gas. This is just one of the reactions that we're going to investigate today as we try to shore up an understanding of how the contributions of Joule, Boltzmann, and their contemporaries can be combined to create a method for predicting which reactions we can expect to take place and which we can expect not to. Let's get started. Enthalpy and entropy. Heat and randomness. We just spent 2 lectures looking at how chemists view these two seemingly disparate and often misunderstood properties of matter. We saw how many familiar processes are driven forward by the release of chemical potential as heat, making reactions exothermic. The most prevalent example of this was the formation of stronger bonds between atoms, building larger molecules to release heat to the surroundings in accordance with the first law of thermodynamics. We also saw how increasing the randomness of a system seems to drive other processes. We considered processes like the vaporization of water. The explosion of nitroglycerin is another great example of how this thermodynamic force powers some other familiar reactions. But there's a battle brewing, one between the forces of enthalpy and entropy. All drama aside, the question probably entered your mind already. If the natural tendency of systems to lower their overall heat, or decrease their enthalpy, as Joule had observed, and the tendency of a system's entropy to increase, as mandated by Boltzmann's, ever collided, who would win? What happens when exothermic reactions reduce the entropy of a system? And what happens when endothermic reactions increase the entropy of a system? It's a great question. Let's explore that a bit. Before we get to the battle royale between enthalpy and entropy, let's define a new term. Yet another term which has a common meaning, but a little different than that used by chemists. I'm talking about spontaneity. The term spontaneity often invokes thoughts of something starting or happening quickly. But when chemists use the term spontaneous, they aren't referring to speed at all. A spontaneous chemical reaction is very simply one that will proceed to at least some extent without any external assistance. That's it. It doesn't matter how slowly a process happens. It can happen all by itself. It counts. It is spontaneous. The most logical question then is this: can it happen? Do reactions exist which are exothermic, yet entropically disfavored? And are there endothermic reactions which proceed with an increase in entropy? If you stop and think for a moment, the answer should be clearly yes. Consider one of the simplest reactions out there, the one that took down the Hindenburg. The combustion of hydrogen gas with oxygen gas to form water vapor. We know that this reaction releases a tremendous amount of heat, but take a close look at the balanced equation. 2 moles of hydrogen gas combined with 1 mole of oxygen gas to form just 2 moles of water vapor. That is entropically disfavored because the equation tells us 3 moles of gas and starting materials produce just 2 moles of gaseous product. So if entropy has its way, this reaction would not proceed at fixed temperatures and pressures. Yet we know very well that it does. We're in Osmond Lab now to take a look at a reaction driven by release of heat, or an exothermic reaction. Now, to do this reaction, I've got a balloon filled with one of my 2 reagents. In this case, the reagent is hydrogen. Of course, you can see the balloon is buoyant because hydrogen is less dense than air, so I have it tethered to a string here. Now, the other reactant in this process is not in the balloon. It's the oxygen in the atmosphere around it. And when I detonate this balloon using a little bit of heat from a flame, what we'll see is the result of a reaction in which hydrogen and oxygen combine in a 2-to-1 ratio to form H2O. And remember, we discussed that the stoichiometry suggests that entropy is working against this reaction. So let's try to get the reaction started and see if it actually does go forward, meaning it is spontaneous, even though entropy suggests otherwise. Now, before I ignite this, I'm going to put on some hearing protection because I know from experience this reaction is spontaneous and it definitely is going to work. And again, what I'll do is I'll bring a flame next to the balloon, and that's going to do a few things. First, it'll break the balloon, mixing the hydrogen and the oxygen together so they can react. And of course, it will provide that little bit of heat for the activation energy to start the reaction up. And then we'll see if we can get a good look at an exothermic reaction. Here we go. Well, we just observed a spontaneous reaction in which entropy decreased. And we also observed pretty clearly that heat was released from that reaction. Mix some hydrogen with some oxygen, use a spark to initiate the reaction, and you can see clearly spontaneous formation of water vapor, complete with the release of heat that we're accustomed to observing when a fuel like this is burned. Now, in this case, energy is given off as heat, and the reaction progresses with no outside assistance. So, Here, entropy lost the battle. The reaction releases so much heat that the decreased randomness within the system is overcome. Score 1 for enthalpy. How about a different kind of reaction? Let's take a look at solid ammonium nitrate dissolved in water. For the first process, I'm going to use a salt called ammonium nitrate and some water. And we're going to dissolve the ammonium nitrate in the water and observe its effects on temperature, much like we did during our calorimetry experiments back in our earlier lecture. So to begin, I'm going to take some distilled water, which is just purified water. Be sure there's nothing in there at the moment. And this has been out on the bench for quite some time, so I'm going to place the temperature probe in there, but of course I'm not expecting much to change. Let's give that a moment. And, of course, just as we expected, there's not a whole lot of change going on here right now because we're using room temperature water in a room temperature beaker with a room temperature probe. But next, I'm going to add the ammonium nitrate, which will dissolve into the water, and we'll observe how that affects the temperature of this system. And to be sure we get a really good observation of this effect, I'm going to use the entire contents of this bottle. So we'll pour that in. And then we'll stir for just a moment here, and we'll see if we can observe any kind of temperature change here. How about that? A drastic and precipitous drop in temperature. So how is this possible? Right? This endothermic process is happening because this solid, or what was solid, ammonium nitrate, is beginning to dissolve into solution where it's in the liquid phase. So that means that entropically, the process of dissolution is favorable. But obviously, from an enthalpic standpoint, it's really not, because it's absorbing a tremendous amount of heat. But this is a physical process, and we're here to talk some more about chemistry. So let's try one more process, this time one that involves a chemical reaction, and see if we can observe its endothermic nature. Now let's take a look at an endothermic chemical process as opposed to that physical process of dissolving the ammonium nitrate. Now, what I'm going to do first might seem a little unusual. I'm going to take a board here, a little piece of wood, and sprinkle just a bit of water onto that board. And next I'm going to run a reaction in a beaker placed on that board. So let's go ahead and just put it there now, make a mess. There we go. What I'm going to do is run a reaction between two solids, barium hydroxide and ammonium thiocyanate. And we'll observe what's going on inside the beaker, and then we'll observe what's going on outside the beaker and see what that tells us about this reaction. Let's begin with our ammonium thiocyanate. Next, I'm going to add the barium hydroxide. And because those reagents are in the solid phase, I'm going to have to stir them for a bit to get them in contact, give them a chance to react. If you're watching very closely, you'll notice that it's starting to get a little bit slushy in there, almost as though some kind of liquid is forming. And I'm going to continue this for a few moments and make sure that the reaction has a chance to run to nearly completion. Okay. At this time, I'm just going to keep stirring for a little while. And if we wait long enough, we'll be able to make some very interesting observations. So at this point, you can begin to see that the product of this reaction clearly has some liquid in it. And what does that tell you about the entropy of this overall process for this system? Well, we went from two solids to a product that contains liquid, which means entropically, this process is quite favorable. However, from an enthalpy standpoint, I can tell just by grabbing this beaker that it's very, very cold. In fact, in this case, it's so cold that I've frozen the beaker and the board together. So again, one more very interesting process here in which it seems that entropy has won the battle, and this reaction actually proceeds even though it is endothermic. So in this case, it's clear that the heat or enthalpy of the system actually increased, but dissolution increased the randomness or entropy of the system. It seems like entropy wins in this case. Now, this process and others like it are used in portable cold packs carried by athletic trainers and emergency medical technicians. A small pouch of the undissolved salt is isolated from water, which is itself contained within a second bag. The act of breaking the seal of the internal salt container allows dissolution to take place, and the endothermic process is underway. If we think of the entire ice pack as the system and your injured ankle as the surroundings, it should come as no surprise that your joint begins to feel cold because of the endothermic dissolution proceeding under the more powerful influence of entropy. So clearly, there are not only plenty of processes for which enthalpy and entropy are working against one another, but there's no guaranteed winner when they are opposed. But so far, our thought experiments haven't been able to tell us which reactions will be spontaneous and which will not. For that, we need to invoke the work of J. Willard Gibbs, an American-born scientist and a contemporary of both Joule and Boltzmann. Gibbs spent nearly his entire academic career, both student and researcher, at Yale University in New Haven, Connecticut. Throughout the late 1800s, Gibbs made numerous contributions to the science of thermodynamics. Arguably, none of his offerings was greater than this: his equation for what has come to be known as the Gibbs free energy change for a process. The Gibbs free energy gives us a way to combine enthalpy and entropy mathematically to determine once and for all, is the standard molar energy change for a process positive or is it negative? During this lecture, just as before with enthalpy and entropy, we'll be concerning ourselves with standard free energy changes, meaning that these energies are determined at 298 Kelvin, about 77 degrees Fahrenheit, and 1 atmosphere of pressure. Of course, these values can vary with conditions, but delta G is a very good indication of the overall behavior of processes near standard conditions. A positive free energy change means that the reaction absorbs energy overall, so it's not going to take place without some outside assistance in the form of energy input. Therefore, we would call a reaction like this non-spontaneous. But a negative energy change means that the reaction will release energy to its surroundings and will happen all on its own, making it spontaneous. This is the equation that changed everything for Gibbs, the free energy equation. What's interesting about the equation, of course, is that it includes a term for enthalpy and a term for entropy, unifying these two forces and helping us to divine which one wins out in a conflict, or exactly how much each one participates in defining the spontaneity of a reaction. Delta G, of course, is the free energy term itself, and that is equal to a term equal to the enthalpy change, so as enthalpy goes, so goes free energy, minus the entropy change modified by the absolute temperature. What's interesting about this is that this lets us know that entropy's contribution to the spontaneity of a reaction is modified by the temperature, so it is temperature dependent, whereas enthalpy change, according to this equation, is not, which means that temperature itself will have a profound effect on whether reactions will take place or not. We'll look at that a little bit more later. But we can go even farther than simply predicting if a reaction will be spontaneous always, never, or at higher or lower temperatures. We can take Gibbs' equation to the extreme and actually determine the magnitude of the standard molar free energy change for a particular compound. So the standard free energy change for any process can be calculated so long as we know three important things. We need to know the standard molar enthalpy, standard molar entropy of the reaction, and the temperature at which it's run. So let's do that right now and calculate the standard free energy change for this process, the conversion of graphite into diamond. We're going to ask the question, is this a spontaneous process at or near conditions that we would encounter in a room here on Earth, about 1 atmosphere, standard temperature and pressure? Well, to begin our calculation, let's consider this. The enthalpy change for that reaction is, of course, simply the heat of formation of the product diamond minus the heat of formation of the starting material graphite, which I can get from tables. And when I do that, I can determine that the standard enthalpy change for the reaction is 1 mole times 1.88 kilojoules per mole, minus, of course, 0, because, remember, graphite is the standard state of carbon, so carbon will always look like that at 1 atmosphere of pressure and standard temperatures. So, let's run our unit analysis. Looks like we're properly set up here to get an answer in kilojoules And that answer is plus 1.88 kilojoules. That tells us that this particular reaction is an endothermic reaction. It's going to require heat to run. Now, the next thing that we need is we need to know the entropy associated with the reaction. And we've also already learned how to do this, how to get it. We simply take the standard molar entropy of the product, subtract from that the standard molar entropy of our starting material, and again, we get these values from tables. That for diamond is 2.43 joule per mole Kelvin times a mole, minus that of graphite, which is 5.69 joule per mole Kelvin, also times 1 mole from my stoichiometry here. And I can determine the actual change in entropy as this process takes place. Canceling out my moles, canceling everything else out, gives me joules per Kelvin. The answer? Negative 3.26 joules per Kelvin. That tells me that this particular reaction has got a negative entropy change. In other words, it's not being driven by entropy either. So we've got two of those important values here in the enthalpy and entropy for this process. But I promised you a third one, right? And we all know what this is because we're dealing with Gibbs free energy. I've got to include the temperature in the calculation as well. So let's put these numbers in and see what happens at 298 kelvins, about room temperature. Our standard free energy change for the reaction is 1.88 kilojoules. That's our enthalpy. Minus the temperature times the entropy. So the temperature defines the contribution of entropy. But of course, in this case, the entropy is negative, and subtracting a negative number means entropy is not going to be helping us very much. In fact, when we run the numbers, what we discover is, oh, wait a minute, I have a problem, don't I? I can't run my numbers yet. My unit analysis has saved me from making a terrible mistake. Kilojoules minus joules can't happen. I need to have similar units if I'm going to subtract them from one another. And that means I've got to convert my entropy into kilojoules per Kelvin. Now my unit analysis lets me know that I've got it right. So I save myself by checking the units every time on every equation. Okay, let's run the numbers now. What we determine is that we have a plus 2.85 kilojoule per mole standard free energy change for the conversion of graphite into diamond. This means that the process as I've written it here is very unfortunately not spontaneous at room temperature. That means it doesn't matter how long you stare at that pencil lead that you've got on the countertop, it's never going to turn into diamond. Sorry. So just as we can estimate things like enthalpies and entropies using our knowledge of chemistry, we can also get a rough estimate of how the free energy of a system will behave simply by knowing the signs of those changes. For example, here's my Gibbs free energy equation again. Delta G is equal to delta H minus T delta S. Now, temperature is absolute, so it's always positive. We have to use kelvins in this equation as our temperature term. But delta H and delta S can both have varying signs, which leads to 4 possible permutations of delta H and delta S signs. And from those 4 permutations, we can actually begin to tell a little bit about how temperature will affect spontaneity in reactions. For example, let's say I have a process in which delta H is positive and delta S is negative. Well, in this case, delta H is going to be working against spontaneity, right, because it's going to create a positive contribution to delta G. And entropy will be doing exactly the same thing. It's going to slow the reaction down, or rather it's going to decrease its spontaneity because a negative entropy is being subtracted. So in the case of a positive enthalpy and negative entropy change for a process, that process can never be spontaneous at or near standard conditions. An example of this is the formation of diamond. Right? We simply can't expect pencil lead to turn into diamond on a countertop. If, however, delta H is positive, but so is delta S, that means that delta S will actually be contributing to spontaneity. And remember that delta S's effect is amplified at higher absolute temperature. So in this case, we'll have a reaction which is more spontaneous at higher temperatures. Simply by increasing the temperature, I can anticipate that I'll speed the reaction, or rather, not speed the reaction so much as make it more spontaneous. Remember, spontaneity doesn't mean speed. An example of this would be the melting of ice, very familiar process to us all, which we know only happens when the temperature is sufficiently high. Now, in situations where we have a negative enthalpy, this time enthalpy is contributing to spontaneity. The more heat that's released, the more spontaneous a reaction will be because that will create a more negative delta G. And if we have a positive entropy change going along with it, Remember, entropy is subtracted, so a positive term here means a greater term being subtracted and an even greater negative number. To put that more simply, when the delta H is negative and the delta S is positive, a reaction will always be spontaneous at or near standard temperatures and pressures. Well, a good example of that is one that we're very, very familiar with, the combustion of propane. Propane and oxygen will always combine to spontaneously form carbon dioxide and water. It's a question of how long it will take, but never whether it will happen or not. Propane and oxygen are destined to become carbon dioxide and water. Now, our fourth set of circumstances would be if we have a negative delta H, which contributes to spontaneity, but a negative delta S, which is working against us. So in this case, to minimize the effect of entropy, we'd have to lower the temperature to make the reaction more likely to be spontaneous. In other words, it's spontaneous at low temperatures. An example of this reaction is the combustion of hydrogen. Remember that combusting hydrogen and oxygen together creates only 2 moles of water vapor, which is entropically disfavored. So, at lower temperatures, this reaction is actually more favored. So free energy combines the enthalpy and entropy considerations, giving us a unifying equation that can help us to explain why propane burns across a wide range of temperatures, or why water boils at 100 degrees centigrade. The impact of Gibbs' equation is indisputable. His free energy equation gives us a way to quickly and easily predict which reactions will be spontaneous and which will not over a range of conditions. So let's summarize what we just accomplished in this lecture. First, we defined the term spontaneous as it's used in chemistry, meaning a reaction or process which will take place without energy input from outside of that system. Then we reminded ourselves about Joule's observation that exothermic reactions, those that release heat, tend to happen spontaneously, and Boltzmann's assertion that increasing randomness can also drive a process or reaction forward. After that, we took a moment to consider the possibility that enthalpy and entropy don't always work cooperatively. We explored a few familiar chemical reactions in which this is the case, including the combustion of hydrogen gas, in which enthalpy trumps entropy, and the dissolution of ammonium nitrate, in which entropy comes out the victor. But we didn't stop there. We took a page from the book of one J. Willard Gibbs, whose free energy calculation gives us a mathematical tool to predict not just if a reaction is spontaneous, but exactly how powerful the driving force behind a given reaction is. Our brief introduction to the concepts of chemical thermodynamics is winding down, but that doesn't mean that we're done with the concepts of enthalpy, entropy, and free energy. Quite the contrary. These forces of chemical and physical change will be with us for the rest of the course, starting with our very next topic, favorable energetic forces that hold molecules and atoms together, intermolecular forces.